Welcome to the fourth session of Basics of Remote Sensing. Here we will discuss about sensor and data products. It is to know about the scanning system during data acquisition and to know about different data products globally and in our Indian scenario. Scanning system in remote sensing. In remote sensing, different types of scanning systems are followed by the sensors. If the scene is censored point by point along successive lines over a finite time, it is called scanning system. Basically, two modes of scanning systems are followed. One is across track scanning system or along track scanning system. Across track scanning system is also called as mechanical or whisk broom scanning, whereas along track scanning system are called as push broom scanning system. In this image, you can see how it is called as a whisk broom. Here we can see an electromechanical satellite sensor is having a system of scanning across the movement of satellite. So you can see the flight direction and the scanning system will be working across to this flight direction. Whereas an along track scanner, we can see it is a kind of push broom concept. We can see just like a swiping along the flight direction or the path direction. It is otherwise called as an electronic satellite sensor. How they are functioning, that we can see in the coming slide. So the whisk broom scanners or across track scanners, they consist of detector arrays with a single detector with a rotating mirror system. Here this rotating mirror system will be functioning, which is controlling the field of view. That means the total angle scanned by this system, as well as the instantaneous field of view, that is IFOV, that is the opening angle of that sensor, which controls the spatial resolution of a particular data. Here this rotating mirror is performing across the path of flight direction or satellite movement or across the SWAG. In a push broom scanners, detector arrays with a linear array of thousands of charge coupled devices in a linear camera records entire line instantaneously. There is no moving part like we have seen in a whisk broom scanner. Generally, push broom scanner receives a better signal level with increased dwell time. They are also possess less geometric distortion in along track scanners. Comparison of a whisk broom as well as push broom scanning techniques. In a whisk broom, across track scanners uses a mirror to reflect light into a single detector, whereas in a push broom, the image is collected one line at a time with all of the pixels in a line being measured simultaneously. In a whisk broom scanner, the mirror moves back and forth to collect measurements from one pixel in the image at a time. In a push broom scanner, it receives a strong signal than a whisk broom scanner because it looks at each pixel area for longer. One of the drawbacks with push broom sensors is that the detectors in the push broom can have varying sensitivity. Almost all the Landsat sensors prior to Landsat 8 use the whisk broom design, whereas the OILA instrument on Landsat 8 uses a push broom design. We will come to know more about the Landsat 8 data in our coming slides. Sensors. Basically, we are having passive sensors and active sensors. In passive sensors, external source of radiation in the form of sunlight, which falls on our Earth's surface, will be emitted back or reflected back from our Earth's surface, is captured by the satellite sensors like multispectral sensors as well as hyperspectral sensors. In multispectral sensors, few number of bands are there, whereas a hyperspectral sensor possesses more number of bands. In an active sensors, the sensor emit a radiation themselves, which will be reflected back from our Earth's surface and captured by these sensors. LIDAR sensors and radar sensors are few examples of active sensors. There is no external source of radiation in this case. Digital sensors. The most common type of remote sensing instruments are the digital sensors, panchromatic sensors as well as multispectral sensors. Remote sensing at this part of electromagnetic spectrum from visible to infrared is collectively known as optical remote sensing. Thermal as well as microwave remote sensing is the other in longer wavelength. Hyperspectral sensors are also fairly common with narrower bands. Panchromatic data. Collection of data in a single band of electromagnetic spectrum, normally within 0.4 to 0.7 μm or wider range of electromagnetic spectrum, are called as panchromatic data. Mostly, the panchromatic data possess a high spatial resolution. Multispectral data. Collection of data in multiple wider bands, starting from our visible to near infrared, shortwave infrared, and up to thermal infrared. Different types of bands will be there in specific wavelength. Hyperspectral data. Collection of data in dozens or hundreds of narrow as little as 0.01 μm in spectral bandwidth for each spectral bands. Such kind of data we call it as hyperspectral data.
Let's see how the entire imaging system works. Charge coupled device sensors are used widely in digital cameras and other light sensing instruments. The energy from an illumination source being reflected from a seen element that we can see in this picture. The first function performed by the imaging system is to collect the incoming energy and focus it onto an image plane. If the illumination is light, the front end of the imaging system is a lens which projects the viewed scene onto the lens focal plane. The sensor array, which is coincident with the focal plane, produces outputs proportional to the integral of the light received at each sensor. Digital and analog circuitry sweep these outputs and converts them to a video signal, which is then digitized by another section of the imaging system. I have few questions for you. Question number 1. Whisk broom scanner has option 1 a long track scanning, option 2 a cross track scanning. What is the answer? A cross track scanning. Question number 2. Which among is an active sensor? Option 1 hyperspectral, option 2 radar, option 3 multispectral. What is the answer? Option number 2 radar. Now we will check where do we find the data. This is a user order processing system by NRSE. For all the Indian remote sensing satellite, we can go to this website after creating a login ID and password with the credentials. You can search for various Indian remote sensing satellite data. This is Bhuvan website, an Indian geo platform of ISRO. Here freely available Indian remote sensing satellite data we can search and download. Other than this, various thematic products related to the remote sensing and GIS are available through Bhuvan portal. A user can log in, then proceed for the downloads. This is a USGS website, Earth Explorer, from which we can download global remote sensing data which is freely available. Similar to this, we are having Alaska, asfalaska.edu. It is supported by NASA Earth data, through which some of the digital elevation model with high resolution can be downloaded. Earth data login supported by NASA gives an archival of almost all freely available global data set which has a wide coverage related to atmospheric science, oceanic science, land surface data, temperature data, and many more. After creating a particular login ID, anybody can go through this website and freely download the required data. This is European Space Agency Copernicus website, from which we can download the satellite imageries by European Space Agency like Sentinel. They are having wide applications in various aspects of remote sensing. Now let's understand more about a satellite data and their bands, how they are useful for us in our various applications. Here you can see how a spectra behaves. Every object on our Earth's surface, they are having a specific spectral signature. Otherwise, every object, they are having a particular reflectance property and absorption property. If you see a plant or a vegetation, with our normal eyes, we are seeing it in green color. Why? Because our retina can identify the visible range of light in our electromagnetic spectra. So our sunlight, it is having blue, green, red, infrared rays. A vegetation or a plant, it absorbs the blue, red lights and it emits green and infrared. If you closely observe the spectral signature is having a reflectance in this graph at point 6, where we are having the reflectance property of the plants in green light, and again we can see a reflectance which is in maximum, that is in the range of infrared. So a satellite sensor which can record the light, the information, the reflectance property and absorption property of a material in green as well as in infrared. Once we use satellite data with different bands which is representing the infrared rays also in their particular range of wavelength, we can see the property of vegetation in infrared band. That is how many of us, when we see a satellite imagery in a hoarding, in a display, where you might have seen that vegetations are in red color. So you might have asked yourself how in a satellite imagery the vegetation is seen in red color. So as an image analyst, as a user, the person have used that infrared band in our satellite data. He has put that particular infrared band in the display, red color. Normally we are having the display in RGB, red, green, blue sequence. Person who is analyzing the vegetation, he can differentiate various vegetation by adding an infrared band in the red color gun, which is more sensitive for our eyes to interpret or differentiate the different types of vegetation by seeing it. You might have also heard the term called false color composite. So this is why we are seeing in the satellite imageries in a display in hard copies, vegetations are normally represented in red color, and we are calling that it as false color composite imagery. Now we will try to relate how these electromagnetic spectra with respect to various bands. Here I am trying to convey you band 1, 2, 3. How they are represented? We can see the band 1 is representing the blue range of visible spectra. Band 2, they are representing the green range, and band 3 towards the red range. If you see in the right side example, it is an example of Landsat TM data where we are having total 7 bands, and they are arranged in a sequence where you can see a difference. After 5 it is given 7, then 6. That is based on their data arrangement. Here we can see the blue band. It is starting from 0.45 to 0.52, which is representing the electromagnetic spectral blue light, followed by green, red, near infrared, shortwave infrared, thermal infrared, like that. So in generally, different satellite data, they are having different number of bands. Each bands will be representing our electromagnetic spectra wavelength. You see in this slide, you can see the electromagnetic spectra over which we have drawn few blocks. These blocks are representing various satellite imagery data bands. You can see in the from the bottom 1, 2, 3, 4, 5, 7, 6 arrangement. So the band 1, it is represented in the blue light. Band 2, that is representing a green, then red, infrared, following that. If you see in the top, the red blocks, that is representing Astro data band, whereas the bottom we were seeing Landsat ETM data. In Astro data, we can see the band number 1, it is placed in the green spectra. If you see in the bottom, in the table, the wavelength, spectral range of first band, you can read there it as 0.52 to 0.60. That means that particular band is representing the green wavelength or spectra in our electromagnetic spectrum. So here we can differentiate Astro data, it is starting with a green band. There is no blue band for Astro data. Whereas our Landsat ETM data, it is starting with band number 1, which is representing a blue band. That we have seen already in the earlier slides. So this is how, as a user, we should understand what are the different number of bands in a satellite data, how each band they are positioned in what spectral range, because as an application part, various materials we will be extracting the information based on their reflectance and absorption character in these spectral ranges. A user gets the data in various units. It may be represented in dN, radians or reflectance. dN is the digital number, that is the average of radians with the reflectance of a smaller area. Radians, how much light the instrument sees from the object being observed. Whereas a reflectance compares the amount of light coming off the earth to the amount of light coming into the earth from the sun.
Now we will try to understand about different data products. Indian remote sensing satellite products having high resolution 2.5 meter and better data are available. Cartosat 2S series having 0.65 meter panchromatic and less than 2 meter multispectral data are available. Under medium resolution from 5.8 meter to 56 meter, Indian remote sensing satellite products List 3, AWIFS, List 4 are giving a good range of satellite products for analysis. Here we can see a very good spatial resolution data, high-tech city area of Hyderabad, as well as in a List 4 multispectral view of Mumbai, as well as List 3 view of Mumbai. Through this you can compare different spatial resolution of the data. List 4 data, they are having spectral bands ranging from 0.52 to 0.86, and list 3 they are having 0.52 to 1.70 spectral bandwidth. We are also having low resolution data which cover a large area in a scene with a spatial resolution 360 meter and coarser. Coming to the global data series, Landsat missions, they are having the data from 1978 onwards with Landsat 1, and currently from 2013 onwards Landsat 8 is covering our entire globe and giving the data. Various applications of Earth observatory studies are done by these Landsat missions.
Landsat 8, otherwise Operational Land Imager OLI, and Thermal Infrared Sensor. Here we are comparing a Landsat 7 data and Landsat 8 data. We can see the band number informations and their respective spectral bandwidth and their spatial resolution in this table. Landsat 8 data, which is widely used in various remote sensing applications, having 11 number of bands, which include coastal aerosol band, blue band, green, red, near infrared, 2 shortwave infrared bands, panchromatic band with 15 meter spatial resolution, and thermal infrared bands having acquisition in 100 meter and resampled and getting for the customers in 30 meter. Astrodata, advanced spaceborne thermal emission and reflection radiometer, having a wide application in the field of geoscience, especially used for alteration mapping purpose because of availability of shortwave infrared bands. Most of the alteration mineral they are having the specific reflectance and absorption character in the shortwave infrared region, which is widely used for various geological mapping and mineral investigation purpose. There are various Astral products are available. As we explained earlier, they are in DN, radiance and reflectance data. Other than that, we are having the digital elevation model, that is Astral GDEM, is also available. Sentinel-2 data. Comparing with the Landsat 8 data, Sentinel-2, they are having a 10 meter spatial resolution band in the visible range and near infrared, which makes popularity for this data for various remote sensing applications. These are the specifications of Sentinel data. As we have seen earlier, Landsat 8 with 11 number of bands having mostly with a 30 meter spatial resolution. Here if you see the band number 2, 3, 4 and 8 are having a spatial resolution of 10 meter, which will help us to identify the features on the Earth's surface easily. That's why these data are widely used nowadays. This is a comparison of Landsat 8, Aster and WorldView 3 data. You can see different bands which are related with respect to the spectral wavelength in the electromagnetic spectrum. L2, Landsat 8 and Landsat 7 data. Each data they are having specific band numbers representing various electromagnetic spectral wavelengths which are used for our various applications with the remote sensing data. Coming to the hyperspectral spaceborne data, Earth observation EO1 Hyperion data is popular among these. They are having a 30 meter of spatial resolution with more number of band representation. That is why we are calling them as hyperspectral data. It is widely used for various spectral mapping purposes. Digital elevation model. There are different digital elevation model data available. Shuttle radar topography mission SRTM, Aster GDEM, CARTODEM are some of the examples for digital elevation models. Through digital elevation model, we can identify the elevation of the terrain as well as we can prepare slope map, aspect map, hillshade map, which are very much useful for identifying structure, preparing geomorphology map, to prepare contour maps, etc.
Thank you for watching. This is the end of the current session, and the next session is on Introduction to Digital Image.